Modules and Homological Algebra, Lecture 17, Monics, Epics, Projectives, and Injectives. Let us start with the definition of a monomorphism. Let C be a category and alpha be a morphism in C from I to J. Definition: we say that alpha is a monomorphism, also known as a monic, provided that for any object K in C and for any morphism beta and gamma in C from K to I, the condition that alpha composed after beta is equal to alpha composed after gamma implies that beta is equal to gamma. As we will see on the next slide, this notion is a categorical abstraction of the notion of an injective map. And the advantage of this formulation is that the formulation in the definition of a monomorphism is defined in terms of morphisms with no reference to elements of the underlying sets. So the motivational example, monomorphisms in sets. Example, a morphism in sets is monic if and only if it is an injective map. Indeed, assume that F is a map from X to Y, which is injective, and let G and H be two maps from Z to X, such that the composition of F after G is equal to the composition of F after H. If G and H are different maps, then there should exist an element Z in the set Z, such that G of Z is not equal to H of Z. Then, from the condition that F is injective, we will get that F applied to G of Z should be different from F applied to H of Z, and this contradicts our assumption that F after G is equal to the composition of F after H. And so it proves that any injective map is monic. Conversely, let F be a map which is not injective. Then there should exist two different elements A and B in the set X, such that the value of F at A is equal to the value of F at B. Let G be a map from X to X, which sends all elements in X to A, and let H be the map from X to X, which sends all elements of X to B. So since F has the same value on A and B, it follows that the composition of F after G is equal to the composition of F after H, while the maps G and H are clearly different. So this shows that any non-injective map is not monic, and completes the proof in our first example. Now let us describe monomorphisms in the category of all groups. So example 2, a morphism in the category of groups is monic if and only if it is an injective map. One direction, namely the fact that any injective homomorphism is monic, follows directly from the corresponding statement in sets. So this is because any homomorphism of groups is actually a map between the underlying sets, so any injective homomorphism of groups must necessarily be monic because it is monic already as a map between sets. To prove the converse, let phi be a non-injective group homomorphism from a group G to a group H. Then the fact that it is not injective means exactly that the kernel of phi, which is a normal subgroup of G, is not equal to the trivial subgroup, so the kernel is non-trivial. Let psi be the homomorphism from the kernel of phi to G given by the natural inclusion. Let eta be the homomorphism from the kernel of phi to G, which sends the whole kernel of phi to the identity element in G. Since the kernel is non-trivial, psi and eta are different homomorphisms, but directly from the definition it follows that the composition of phi after psi is equal to the composition of phi after eta and is equal to the trivial map. Therefore, phi is not monic. and this completes the proof in our second example. The third example, let us describe monomorphisms in the category of semigroups. Example 3. A morphism in the category of semigroups is monic if and only if it is an injective map. Again, one direction follows directly from sets. The fact that any injective semigroup homomorphism is monic follows directly from the corresponding statement for the category of sets, because any homomorphism of semigroups is actually a map between the underlying sets. To prove the converse, let phi be a non-injective semigroup homomorphism from a semigroup S to a semigroup T. Then there are two elements A and B in S which are different, but such that the value of phi at these two elements coincide. Consider the free semigroup on one element, so we choose as this free semigroup the additive semigroup of positive integers, and then the basis of the semigroup is the element 1. Then we have the homomorphism psi from this free semigroup to S, which is uniquely defined by the condition that it sends the basis element 1 to A. And we have another homomorphism eta from this semigroup to S, which is uniquely defined by the condition that it sends the basis element 1 to B. By the free property, sending the basis element uniquely extends to a homomorphism. Then, of course, directly from the definition, psi and eta are different because A and B are different. But again, if we compose psi and eta with phi, then phi after psi is equal to phi after eta, because the value of phi after psi at the identity is equal by definition to phi of A, which is equal to phi of B, and this is equal to phi of eta of 1. And this means that phi after psi and phi after eta send 1 to the same element, which means that they coincide again because 1 generates the semigroup of all positive integers with respect to addition. This shows that phi is not monic. Here are some other examples. Example 4. A morphism in rings is monic if and only if it is an injective map. So that any injective morphism in the category of rings is monic follows directly from the corresponding statement for sets, and the converse is proved similarly as for semigroups, looking at homomorphisms from the free ring Z of X on X to our ring. Example 5. If R is a ring, then any morphism in the category of all left R modules is monic if and only if it is an injective map. Indeed, that any injective morphism in this category is monic follows from the corresponding statement for the category of sets, and the converse is proved similarly to groups, because if we have a module homomorphism which is not injective, then the kernel of this homomorphism is not 0. This describes several examples of classification of monic morphisms in various categories. Now let us go to epimorphism. Let C be a category, and let alpha be a morphism in C from I to J. Definition: we say that alpha is an epimorphism, also known as epic, provided that for any object K in C, and any morphisms beta and gamma in C from J to K, the condition that the composition of beta after alpha is equal to the composition of gamma after alpha implies that beta is equal to gamma. In other words, alpha is right cancelable. Remark: as we will see on the next slide, this notion is a categorical abstraction of the notion of a surjective map. And similarly to monomorphisms, the advantage of this notion is that it is defined purely in terms of morphisms with no reference to elements of the underlying sets. So, example 1, a morphism in the category of sets is epic if and only if it is a surjective map. Indeed, assume that a map F from a set X to a set Y is surjective, and let G and H be two maps from Y to Z, such that the composition of G after F is equal to the composition of H after F. If Y is an element of Y, then, since F is surjective, there is an element X in X such that F of X is equal to Y. Now, from the condition that G applied to f of x is equal to h applied to f of x, we have that g of y is equal to h of y. This is because f of x is equal to y, and this is true for all y, which means that g is equal to h. And this proves that f is an epimorphism. Conversely, assume that f is not surjective. Then there is an element y in Y which is not in the image of F. Let Z be the set with two elements, 0 and 1, and let G be any map from Y to Z. Let H be the map from H to Z, which is obtained from G by changing the value at one element, namely at the element Y. There are two possibilities to choose the value at Y, and we take for H the different value. So H and G are different maps. But since Y is not in the image of F, the composition of G after F is equal to the composition of H after F. So F is not epic. Other examples. Example 2. Let R be a ring. Then a morphism in the category of all R modules is epic if and only if it is a surjective map. Indeed, if phi is a surjective homomorphism from an R module N to an R module N, then the fact that this homomorphism is epic follows directly from the corresponding statement in the category of sets. Conversely, let phi be a non-surjective homomorphism from a module N to a module N. Let pi be the natural projection from N to its quotient modulo the image of phi. And let psi be the zero map from N to its quotient modulo the image of phi. Then phi is different from psi, since the image of phi does not coincide with N. While the composition of psi after phi is equal to the composition of pi after phi, and they both are equal to the zero homomorphism by construction. So this shows that our phi, which is not surjective, is not epic. Example 3. A morphism in the category of groups is epic if and only if it is a surjective map. One can Google for the proof of this statement. This is a non-trivial statement with a fairly non-trivial and not very short proof. This statement is originally proved by Schreier. Here is one more example, and it turns out that epimorphisms in the category of monoids are not necessarily surjective maps. Example 4. The natural embedding of the monoid of all non-negative integers with respect to addition into the monoid of all integers with respect to addition is an epimorphism in the category of monoids. And of course, this embedding is not a surjective map. So let M be a monoid and phi and psi be two monoid homomorphisms from the monoid of all integers to the monoid M. Assume that the composition of phi after our embedding iota is equal to the composition of psi after our embedding iota. In particular, this means that phi of 1 is equal to psi of 1. Since our monoid set of all integers is in fact a group, and -1 is the inverse of 1 in that group, we have that phi of -1 should be equal to psi of -1, this should be -1, and this is the unique inverse of the common value of phi of 1, which is equal to psi of 1. Hence, phi is equal to psi because, as a monoid, the group Z is generated by the elements plus and -1, and the values of phi and psi on both these elements coincide. So this implies that our morphism iota is an epic. In particular, we see that this iota is both monic because it's injective and epic, but it's certainly not an isomorphism because it's not surjective. Okay, let us now discuss the categorical notion of a projective object. Let C be a category. Definition: an object P in C is called projective, provided that, for any objects J and K in C, any epimorphism alpha from J to K in C, and any morphism beta from P to K, there is a morphism gamma, not necessarily unique, from P to J in C, such that beta is equal to the composition of alpha after gamma. Here is the diagram. This is our object P. Any epimorphism alpha from any J to any K, and a morphism beta from P to K. There should exist gamma from P to J such that this diagram commutes. In other words, the map of composing with alpha on the left, and this is a map from CPJ to CPK, the map between these sets should be surjective for any epimorphism alpha. And again, we see that this condition is defined purely in terms of morphisms. There are no things about elements of any sets, but it can be reformulated in terms of a surjective map, but then it's a surjective map on the morphism sets. Here's an example. Example 1. Any initial object of any category is projective. So this follows directly from the fact that if you have an initial object P, then CP something is a singleton for any something, and so the map of composing with alpha from CPJ to CPK is bijective because it's a map between singletons. Example 2. 3 groups are projective objects in the category of groups. Indeed, we know that in the category of groups, epimorphisms are surjective. Let f of x be a free group on some set X, alpha a surjective group homomorphism from a group G to a group H, and beta be some homomorphism from f of x to H. Then for any element x in X, we can choose an element AX in the preimage under alpha of the element beta of X. This is well defined because alpha is surjective. And now we can use the free property of f of x to construct a homomorphism gamma from f of x to G, which sends this element x to our chosen AX. By construction, we will have that this homomorphism gamma, when post-composed with alpha, gives beta. This follows directly from this condition. Now let us talk about projective objects in module categories. Theorem: let R be a Noetherian ring. Then projective objects in the category of finitely generated left R modules are exactly the direct summands of free modules. Proof: let P be a projective object in the category R mod. Let F be a free cover of P. So we have a surjective homomorphism from F to P. So this is surjective, and so it's an epimorphism. Then, by the projectivity of P, the identity map on P, so that's a morphism from P to P, must factor through this free cover. So there is a morphism from P to F, such that composing this morphism with the projection onto P gives the identity on P. This means exactly that P is a direct summand of F. Conversely, let P be a direct summand of F. The same proof as in the category of groups shows that any free module is projective. So it remains to show that any direct summand of a projective module is projective. So we show it as a separate lemma. A direct summand of a projective module is projective. Proof: let P be a projective module which is a direct sum of x and y. Let alpha be a morphism from M to N which is surjective, or that means an epimorphism. let beta be a morphism from x to n. Then we can extend beta to a morphism from p to n by declaring that it is 0 on the summand y. So beta direct sum with 0 is a morphism from p to n. By the projectivity of p, beta plus 0 factors through some morphism gamma tilde from p to n via alpha. So in other words, this morphism beta plus 0 is equal to alpha after gamma tilde, or some gamma tilde from p to n. So if we define gamma as the restriction of gamma tilde to x, we get that alpha after gamma is equal to beta. And this implies that x is a projective module. Corollary: if A is a finite dimensional algebra and E an idempotent in A, then AE is a projective A module. So this follows directly from the fact that the left regular module A, which is a free A module of rank 1, is a direct sum of AE and the module A times 1 minus E. So AE is a direct summand of a free module, which means from the previous theorem that it is projective. Injective objects. Let C be a category. Definition: an object I in C is called injective, provided that for any objects J and K in C, any monomorphism alpha in C from J to K, and any morphism beta in C from J to I, there is a morphism gamma in C from K to I, such that beta is equal to gamma after alpha. So here we have the picture. This is our injective object I. For any monomorphism from J to K and any morphism from J to I, this morphism beta factors through alpha via some morphism gamma from K to I. In other words, the map of precomposition with alpha from CKI to CJI is surjective. So it's important that it's surjective, not injective, for any morphism alpha. And again, the main plus of this definition is that it is formulated purely in terms of morphisms, no reference to any elements of any underlying sets. Examples. Example 1. Any terminal object of any category is injective. Indeed, in the case of a terminal object, the map of precomposition with alpha from CKI to CJI is bijective because it's a map between singletons. Example 2, a very non-trivial example, the additive group of rational numbers is an injective object in the category of all abelian groups. Proof. Recall that all monics in module categories are injective maps. Let A be a subgroup of an abelian group B. So this is our modeling of a monic morphism from A to B. We just realize A as a subgroup of B. Let beta be some group homomorphism from A to Q. Consider the set of all pairs G, F, where G is a subgroup of B containing A, and F is a morphism from G to Q, whose restriction to A coincides with B. Note that the set is partially ordered with respect to the following order. The pair G, F is smaller than the pair G prime, F prime, if and only if G is a subgroup of G prime, and the restriction of F prime to G coincides with F. Clearly, this partially ordered set contains upper bounds for any chain, which is given by the union of elements in this chain. Hence, we can apply Zorn's lemma and deduce that this partially ordered set contains a maximal element G, F. It remains to prove that this maximal element G, F, G is equal to B. And in this case, we can simply take the factorization morphism gamma in the definition of an injective object to be our morphism F. So let us prove that G is equal to B. Assume that G is not equal to B, and let little b be an element of B outside G. Let G prime be the subgroup of B which is generated by G and this little b. If the cyclic group generated by this little b in B intersects our group G trivially, then of course G prime is equal to the direct sum of G and this cyclic group, and we can define the extension F prime of our map F, which is a group homomorphism from G prime to Q, by setting that the value of F prime at B is equal to 0. If NB belongs to G for some minimal positive element n, then we can extend the homomorphism F from G to Q to a homomorphism F prime from G prime to Q by setting that the value of F prime at B is equal to 1 divided by n, F applied to NB. And this contradicts the maximality of G, F, because we now have found a bigger group G prime, F prime, which belongs to our partially ordered set. So this contradiction completes our proof. And some remarks at the end. Remark 1. An abelian group A is an injective object in the category of abelian groups if and only if this group A is divisible. That is, for any element A in A and any positive integer n, there is an element B in A such that NB is equal to A. So we can divide by n. And note how we used this fact for the rational numbers at the end of the previous slide, when we proved that the rational numbers form an injective abelian group. Remark 2. In decomposable projective left modules over a finite-dimensional algebra, which is given as a quotient of the path algebra of a finite quiver by an admissible ideal, are in bijection, of course up to isomorphism, with vertices of the quiver. If we fix a vertex, then the indecomposable projective module corresponding to this vertex has a natural basis which is indexed by all paths in the algebra, of course modulo our ideal, starting from that vertex. Dually, indecomposable injective left modules over a finite-dimensional algebra given as a quotient of the path algebra of a finite quiver by an admissible ideal are in bijection, again up to isomorphism, with vertices of that quiver. The indecomposable injective module corresponding to some vertex has a natural basis indexed by all paths in the algebra, again modulo the ideal, which terminated that vertex. And these two things are dual because they are connected by the following construction. These indecomposable injective left modules are the images of the indecomposable projective right modules under the usual vector space duality of homing into the base field over the base field. Okay, some problems and questions at the end. Question 1. Show that any monomorphism in monoids is injective. Question 2. Show that monomorphisms in C are epimorphisms in the opposite category and vice versa. Question 3. Show that projective objects in C are injective objects in C-op and vice versa. Question 4. Construct up to isomorphism in decomposable projective modules over the path algebra of the following quiver. So we have 3 vertices and 2 arrows from the first vertex to the second vertex and from the third vertex to the second vertex. Question 5. Construct all indecomposable injective modules over the path algebra over the same quiver. Thank you very much and see you next time.